We are at the last part on the mechanisms of heat transfer, radiation. There are two modules to this topic. The first one being fundamentals of thermal radiation. This is the first part of this particular module. It will cover basic concepts, electromagnetic waves and spectrum, the laws of Stefan Boltzmann, Planck's, Wien's and Kirchhoff's, and radiative properties. Previously, in heat transfer by conduction and convection, you know that these mechanisms of heat transfer requires a temperature gradient in some form of matter. However, in radiation, it requires no matter what. It is important in many industrial heating, cooling, and drying processes, as well as energy conversion that involves fossil fuel combustion and solar radiation. Note that all three modes of heat transfer may occur simultaneously, and you must consider the mechanisms in your analysis. But here, in these two modules, we will look at the theories and mechanics of radiation heat transfer only. Basic concepts. First, let's have a look at the solid, particular solid that is initially at Ts, surface temperature is Ts, which is lower than the surrounding temperature. Now, they are separated by a vacuum. There is no conduction or convection. I'm sure you know why. The answer was given earlier. What will happen with time? Well, with time, the solid here will reach a thermal equilibrium with its surrounding due to emission from its surrounding. Is there any thermal radiation from the solid to its surrounding? The mechanism for radiation is associated with the energy released as a result of vibration and electron motions in matter. The vibration is related to that temperature. So the different degrees of vibration will affect the different levels of temperature recorded. All matter at temperatures above absolute zero, which means 0 Kelvin, not 0 degrees Celsius, because 0 degrees Celsius means 273 degrees Kelvin. All matter at temperatures above absolute zero emits radiation, unlike conduction and convection, which occur when there is temperature difference. Energy transfer by radiation is fastest at the speed of light, with no attenuation in a vacuum. Wow! So, for gases and semi-transparent solids, for example glass and salt crystals at elevated temperatures, emission is a volumetric phenomenon. So here's a volumetric phenomena. But in this course, we will look only at the surface phenomena because in most solids and liquids, the emitted radiation from the interior molecules are absorbed by adjoining molecules. In general, radiation is emitted from a solid or liquid originates from a distance of 1 micrometer from the exposed surface. Yes, 1 micrometer. A micrometer is 10 to the power of minus 6 meter. What is the theory of thermal radiation? There are actually two theories. The first one, developed by Maxwell. Radiation is just a propagation of electromagnetic waves characterized by the wavelength lambda and frequency v, or we use f, given by 12.1. Yeah? So Maxwell established this as a result of changes in electronic configurations of the atoms of molecules, where c here is the speed of light in a particular media. It's dependent on the type of medium. C0 is a constant, it's for propagation of light in a vacuum. N here is index of refraction of the medium, which is unity for most gases and air, 1.5 for glass, 1.23 for water. Now note that the wavelength and frequency is inversely proportional. So therefore, a shorter wavelength means there is a larger frequency. Frequency means number of oscillations per second of propagation of an electromagnetic wave, which depends only on the source and independent on the medium through which it travels. The second theory on radiation was developed by Max Planck, stated that radiation is a propagation of a collection of particles, or discrete packets of energy, termed photons or quanta. Each photon or quanta has an energy of hc over the wavelength, where h is the Planck's constant, very small here in joule second. According to 12.2, shorter wavelength radiation possesses large photon energies. Let's look at the spectrum of electromagnetic radiation. The electromagnetic radiation encountered in practice covers a wide range of wavelengths, varying from less than 10⁻10 for cosmic rays to more than 10⁻10 for electrical power waves. The electromagnetic spectrum includes gamma rays, which are produced by nuclear reaction, so shorter wavelength N, X-rays from bombardment of metals with high energy electrons, microwaves produced by special types of electron tubes such as klystrons and magnetrons, that's the other end of the spectrum, radio waves by the excitation of some crystals or by the flow of alternating current through electric conductors. Short wavelength radiation like the gamma rays, X-rays, and the ultraviolet radiation, UV, is of primary interest to the high-energy physicist and the nuclear engineer. The long wavelength microwaves and radio waves with wavelength larger than 10⁵ micrometer are important to the electrical engineer. Now, it is the intermediate portion of the spectrum from 0.1 to 100 micrometer, which includes a portion of the UV and all visible and infrared that is termed thermal radiation, the red colored region. So, a body that emits radiation in the visible range is called a light source, wavelength between 0.4 to 0.76 micrometer. The electromagnetic radiation emitted by the sun is known as solar radiation, wavelength from 0.3 to 3 micrometer. Almost half of it is light, the rest being UV and infrared. Thermal radiation emitted by bodies at room temperature is in the infrared range. Can't see with the naked eye. It's between 0.76 to 100 micrometer. Body starts to emit visible radiation at temperatures above 800 Kelvin. In heat transfer studies, we are concerned only with radiation associated with temperature variations. And thermal radiation emitted results from energy transition of atoms, molecules, electrons of a substance. So, temperature is a measure of the strength of these activities. The higher the strength, the higher the activities of these atom, molecules, electrons, the higher would be the temperature recorded. The magnitude of radiation at any wavelength and the spectral distribution vary with the nature and temperature of the emitting surface. Can two different surfaces at the same temperature emit different amounts of radiation? Well, the answer is there for you to read. We have had a look at black body radiation briefly during the first week of the semester. Let's have a look at it again. It's an ideal body with the following characteristics. A black body absorbs all incident radiation regardless of wavelength and direction. Its absorptivity is unity. It's a perfect absorber. At any particular temperature and wavelength, no surface can emit more energy than a black body. It is a perfect emitter. And although the radiation emitted by a black body is a function of wavelength and temperature, it is independent of direction. A black body is a diffuse emitter. So in the top hemisphere, 180 degrees. There's 360 all around. Stefan Boltzmann law gives the black body radiation emissive power 12.3. You've seen this before during the first week, where sigma is the Stefan Boltzmann constant. It's the sum of the radiation emitted over all wavelengths. The black body serves as a standard for comparison purposes, even though it does not exist. The closest approximation to a black body is achieved by a cavity. Why is a cavity? It's just a small opening, a hole, whose inner surface is at a uniform temperature. So you see here, any radiation that hits the cavity will enter totally, will not be coming out again. So it's a perfect absorber. And any radiation that leaves the cavity is diffuse. It's a diffuse, a perfect emitter. The spectral black body emissive power is the amount of radiation energy emitted by a black body at a thermodynamic temperature T per unit time, per unit surface area, and per unit wavelength about the wavelength lambda. Now, that's a mouthful, huh? It's given by 12.4, yeah, developed by Max Planck. So you see here, the emissive power is a function of lambda and temperature. Yeah, T being the absolute temperature at the surface, and lambda is the wavelength of the radiation emitted. Now, 12.4 is actually valid for any surface in a gas or medium or vacuum. It's plotted here in 12.9 in your eBook. Yeah, variations of black body emissive power with wavelength. Several important features of the Planck distribution, 12.4, and plotted here. The emitted radiation varies continuously with wavelength. At any wavelength, the magnitude of the emitted radiation increases with increasing temperature. So you see, if you choose 10 micron here, yes, the emitted radiation at 100 is lower than that at 300, which is lower than that at 500. The spectral region in which radiation is concentrated depends on temperature, with more short wavelength radiation as the temperature increases. It's more on the short wavelength range. The spectral distribution has a maximum with the corresponding wavelength lambda max, which depends on temperature. So the peak at each temperature depends on the temperature. See, this is at 100 Kelvin. The peak is here. The emitted radiation peak is here, while at 300 is much higher, so on. Yeah. A significant fraction of the sun radiation, which may be approximated by black body at 100 Kelvin, is in the visible region of the spectrum. For temperature lower or equal to 800 Kelvin, emission is predominantly in the infrared region. It's a visible region here. So as the temperature increases, the peak of the curve in figure 12.9 shifts towards shorter wavelength. Yeah, it's joined by the straight line here. You can see that. Yes. And Wien's displacement law gives the maximum wavelength, the straight line, at any temperature by 12.5. Actually, you can get 12.5 by differentiating 12.4 with respect to the wavelength here, yeah, holding the temperature constant. On the other hand, if you integrate 12.4 over all wavelengths, it will give you 12.6, which is the total radiation by black body at all wavelengths from lambda is equal to 0 to infinity. For radiation energy emitted by a black body per unit area over a wavelength band from 0 to some wavelength is given by 12.7, but it does not have a simple closed form solution. So a dimensionless quantity called the black body radiation function is introduced, 12.8. The function represents the fraction of radiation emitted from a black body at temperature T in the wavelength band from 0 to a certain wavelength. Yeah. They are listed in table 12.2 as a function of lambda T. Again, make sure that T is in Kelvin. Yeah. So here, watt per meter squared is the unit. Now, normally we are interested to know the fraction of radiation emitted by a black body at temperature T over a finite wavelength band, not from 0 to some wavelength, but from a certain wavelength to another wavelength. So, you may use 12.9 to obtain that fraction of radiation in that band of wavelength. Colors that we see do not depend on emissivity. Surface absorption and reflections are responsible for our perception of colors. We see blue, red, etc. It's nothing to do with emissivity, but absorption and reflection. Can you explain how?